Hello, everyone, and thank you for attending today's webinar, Designing 6G, Enabling Scalable Mobile Connectivity for Our AI-Driven Future, sponsored by Qualcomm. Before we begin, I will cover a few housekeeping items. On the left-hand side of your screen is the Q&A. If you have any questions during the webcast, please type your question into the Q&A box and submit them to our speakers. All questions will be saved, so if we don't get an answer to you, we may follow up via email. At the bottom of your audience console are multiple application widgets you can use. If you have any technical difficulties, please click on the yellow help widget. Here you can find answers to common questions. A copy of today's slide deck is available for download in the blue resource list widget. Near the end of today's presentation, please take 1 minute to complete the survey that's open on your screen. Your feedback is extremely helpful. An on-demand version of the webcast will be available about 1 day after the event and can be accessed using the same audience link that was sent to you earlier today. I would now like to turn over the event to Heavy Reading's Principal Analyst, Gabriel Brown.
Hey, thank you, Catherine, and hello, everybody. Welcome once again to today's webinar, Designing 6G, Enabling Scalable Mobile Connectivity for Our AI-Driven Future. It is terrific to have you with us. Thank you very much for coming. So the focus today, of course, is on 6G wireless and the design of the next generation mobile network platform. As you heard, my name is Gabriel. I'm an analyst with Heavy Reading. I'm the moderator for today. Heavy Reading, of course, is a part of Omdia, one of the world's largest tech industry research firms. We have two fabulous expert guest speakers with us today, both from Qualcomm Technologies. First of all, I'd like to introduce Dr. Ting Fan Ji. He's a VP of Engineering there at Qualcomm. Ting Fan, welcome. Are you with us? I very much know he is with us, so we'll give him a moment. And also Gavin Horn, Dr. Gavin Horn, a Senior Director of Engineering. Gavin, are you there?
Yes, I'm here. Thank you, Gabriel.
Okay, so Ting Fan's going to take us through the first part of the session. He'll be looking at a standards timeline, a little bit of an outlook for 5G services, some of the key decision points around 6G radio, 6GR and RAN. And then Gavin's going to explore some of the major system architecture options that will shape 6G and a little bit of the migration path from 5G as well. We have a ton of material today, and the speakers are going to move pretty quickly through it. But we are aiming, if we have time, to take some questions at the end. So that's via the Q&A tab on your screen. I have just one slide of introduction, which should be coming to your screen now. So an objective really for the wireless industry is to develop a 6G system that can be funded and operated within the envelope of the current business model, but that can also have a practical application and value from day one. Day one being the term everyone uses for, at launch, if you see what I mean. So there's rightly a lot of focus on learning from 5G and creating a simplified, leaner 6G system. And this is, of course, very pragmatic. It makes a lot of sense from the vantage point of 2025. And this is really where most operators and really most of the industry is in its thinking today. However, at the same time, we all know the world is changing, and it's changing fast and significantly. So we don't really know the detail of services or the economics that are going to prevail 15 years from now. But really, it could be pretty epic. There's a lot of amazing stuff, for want of a better word, tech stuff, that's happening in the world. Virtually all of it is going to be connected. And so what we need to be thinking about is to create a 6G that can meet the demands of advanced at-scale services somewhere around 2040, if historical patterns apply. And that, of course, is going to require a lot of technical ambition and vision to deliver. Now, no question, this is a fine balance, what we need in the near term and the long term. And potentially, I think quite most likely, it means more of a shift to a kind of a continuous development mode. We have this already in the industry, of course, and particularly as you look at 5G Advanced, it's deploying in that way. But that may well become the sort of main model going forward. Now, and so with that, the next few years are going to be very influential on how 6G develops. And certainly, if you want to influence the path forward, now is the time to be active and engaged. That's why we're having this webinar today. I think, from my point of view, at a minimum, that means paying attention to the two 3GPP studies that are now underway in Release 20. So the first on architecture for 6G system, the other on study on 6G radio or 6GR. Now, these are just studies. They're not on their own decisive, but you know how it works, right? The plans are being drawn up, decisions are being made as we speak and as we go over these next year or so for the study and then the first version of standards. So there's not a lot of time to really have an input here. That kind of brings me to the end of my introduction. I've just published a new white paper available for download in the resource section of this webinar console that sets out some of these thoughts in a bit more detail. You'll also see there the PDF slides available. It's a fantastic deck. Lots of detail in it that you can dig through, even if we don't get to all of it in the comments and spoken delivery right now. With that, I'm going to hand over to Ting Fan Ji at Qualcomm to take us through the first section. Ting Fan, if you're there, you're in control.
Thank you, Gabriel, for the introduction. It's super exciting to join you guys in this webinar. And today's topic is how to enable scalable mobile connectivity and drive our AI future. And I think today's webinar is especially meaningful and exciting because we just finished the first meeting of 3GPP run working group design. And there are even some conclusions already made. To our surprise, CP OFDM and DFT spread OFDM will be included in the 6G waveform. So very exciting. And so I think like Gabriel said, decisions are being made. We're quickly working through this 21-month study, and then it will be followed by the work item. So today we have 6 agenda items, and I'm going to cover the first 3. It's how the mobile connectivity has been evolving and what 6G is going to achieve. And then the bread and butter for 6G, for any G, right? So, connectivity and capacity are the key. So without additional capacity or better coverage, there is a really communication network is not going to bring you new services. But then even with different or improved coverage and capacity, what type of services can we get? Is a pipe, the connectivity, the only service? I'm going to discuss all the services we will enable. So, and Gavin will walk you through the architecture, and we'll also jointly come to the conclusion and questions. All right. With that, let's take a little bit of a zoomed out view for mobile connectivity evolution. Right. What we want to show here is mobile transformation is not developed in a vacuum by itself. I think we all know the whole world is evolving, right? From 1G to 6G, now we're talking about. There are bigger picture that's happening, a bigger picture tech evolution. For example, since we're in 2025, no one can have a talk without talking about the AI, right? So that is a major society or technology transformation that we're going through. So you will hear a lot about AI as part of what 6G is trying to solve, and also part of the tools that we'll use to design 6G. So there are these generational technology that's going on, and we will talk about edge compute. We'll talk about agentic AI, XR, robotics, and all those applications later on. So in terms of wireless data or cellular data, what's driving the 6G evolution, right? So the bread and butter, as I was talking about earlier, is the data usage increase. So there is wide consensus that by 2030, we'll still have 3x in terms of mobile data usage growth. And what's behind it? A big part of it is FWA, right? Or it's a mobile broadband. It's for 5G use case. This wireless connectivity is another option now for in broadband home and even broadband to enterprise. And then, of course, we're consuming more data, but more importantly, this AI is growing new data traffic. We're going to through some details later, but here, as you can see, our prediction is 5x to 9x, actually, for the 2023 to 2033. This is the amount of increase we're expecting, for the downlink uplink evolution. So there is still a huge data demand that we have to meet for our 6G design. So, but in terms of how we use data, really the consumer behavior is changing drastically, right? right now, we really have our little square devices with us, and there are hundreds of icons there. We're clicking through these apps, and really, it's a smartphone. It's a main use case, and we are consuming a lot of TikTok videos or YouTube Shorts, if you are me. But the next generation in the user devices are quite different. Instead of clicking through these apps, it's more likely than not, we will have this context-aware AI agent that's orchestrating all the apps or all the tools that serve our purpose, right? Even these days, I think I start to use this voice control for whatever I want to do a lot more compared to, I cannot imagine last year. I will be just talking to my phone so much instead of clicking through apps. So also, it's not only the phone. I don't have my sunglasses with me, but I have this Meta glass for more than a year now. So that's what I wear when I walk dogs. And also when I go on a trip, I wear these glasses. Last time I used it earlier this year. Live translation is not available yet. At that time, I was just using it to look at some of the signs that in foreign language I don't understand, and I ask it to translate. Right? It's all through audio, but because it has cameras, it's extremely handy. And the new features that have been rolling out, which I haven't used yet, is actually this live conversation just with the Meta glasses. Right? So this new form of device form factors will play a big role in terms of consumer behavior and how we drive the cellular users, different traffic need. And the direct result of this usage pattern change is leading to different traffic that we're seeing. For example, instead of a lot more downlink, we'll see quite a bit of uplink. So because, like I said, if I'm streaming my video upward to discuss for the AI agent to consume, you can imagine the uplink traffic will be extremely critical, and the uplink coverage also will be very important. So those are sort of the behavior change that we are expecting. So taking a step back, is 6G is, of course, we just talked about consumer, but it's a lot more than consumer, right? So this is actually the backbone of the society. So it doesn't matter, it's for public safety, it's for industrial revolution, and for consumer, we talk about. The 6G, the importance of 6G is not just sell consumer another device and entertain the users. It's actually going to drive the overall digital economy. So that's the importance. Why all the governments are so focused on leading 6G, because I think everyone realized if you're behind on the cellular connectivity, your overall society will be left behind in terms of technology evolution. So, and at this moment, of course, since AI is a rage, and we know that on the left side, although we draw it in a very small circle, the central cloud AI, right? So this is probably driving a huge fraction of our GDP and investment, our market cap, at least a huge chunk of it is in the central cloud AI. And the role of 6G is to connect that with on-device AI, because their learning is critical, training this large language model is critical, and all those things need to be done in the cloud. But think of the use case when it make an impact to our life is actually inference, right? And the on-device inference, the capability is growing every day. The role 6G is playing is to allow the user and allow the enterprise to seamlessly transition between the on-device and edge cloud and central cloud AI use case. Give you the best user performance and give you the best energy performance as well. So in summary, what 6G will allow us to do is shown in this Venn diagram. So on one hand, we are going to enable agentic AI and extended reality experience. On the other hand, AI will also allow us to increase the network efficiency and provide new services like digital twin. Right? So those are the what AI can bring us, and you can see the intersection in the middle, which is very interesting. Is we can use AI to allow you to have this AI native protocol to allow the service to be adapted according to the use case and to the context, and our network will be smarter and will enable continued user experience. So with that said, here is an overview of where we are in terms of the sausage making process. So like I announced at the beginning, it's super exciting that we just finished the first meeting. And as you can see on the x-axis, we're right after, a little bit after the middle of 25. And there is a consensus that we will finish the spec sometime probably in 2029 and deployment in 2030. So that will be the next 4 years will be critical. The study portion will be almost 2 years, and then followed by 1.5 years, specification. Exactly what the commercial timeline would be is depending on how the ecosystem evolves, right? So we'll see. We don't know yet, but like Gabriel introduced at the beginning, its next couple of years will be very critical. So now let's talk about the coverage and capacity, right? What are the fundamental gains that you will see in 6G in terms of connectivity? So first of all, and this is probably the most important point I want to bring out, is although every G needs new spectrum, right, which is oxymoron if you say the next G, but you don't have spectrum, there doesn't matter how smart you are, as long as the previous generation did not mess up, the amount of gain you're going to see will be limited, or unless the operator has infinite amount of time, money to densify their network, you will not see fundamental gains. So we need new spectrum. But at the same time, in 6G, we are looking much closer at how to enhance existing spectrum band, how to enhance legacy deployment. So you will see a huge emphasis in 6G on existing band enhancement. So that's something that that's essentially it's a low band, mid band, millimeter wave. You will see a lot of enhancement that we're going to introduce. I'm going to give you some concrete numbers a little bit later, and also on the uplink coverage as we talked about before. But 6G is for all bands. So even for operators whose spectrum situation is not like in 2029, you have a bunch of spectrum all of a sudden showing up, hundreds of megahertz. Still, there is a big value in terms of upgrading to 6G. So this is one slide summary of what we want to achieve in 6G. This is still Qualcomm's view, but it's corroborated by other infra vendors, device vendors, chipset vendors as well. So we are expecting about 50% gain in mid-band, both FDD and TDD. Here, one example, we're showing FDD as example of this legacy band. But in TDD band, you should also expect maybe not 50 to 70, but 40 to at least more than 40%. I think we see 40 to 60% gain that you can see, even for SU MIMO, for those of you who are deep in the PHY design, right? So where do we get the enhancement? We'll get some new modulation and coding. We'll get some waveform enhancement. This will be especially important for coverage. We'll also get a lot new MIMO and new data channel designs. And so there are many elements that's contributing to this enhancement. But roughly, if you want to remember one number, is like 50%. Existing band, don't touch your RU, don't touch your RH or antenna system. Just have a baseband DU upgrade, and you get roughly 50% gain. That's the expectation that we have. So, of course, upper mid-band and mid-band will see important gain as well. So given the time limitation, let me actually skip to this slide, where we're showing that the expectation is without densification, if you deploy upper mid-band plus a C-band system, you will see about 5x traffic load that we can support for the minimum, same minimum performance. I think in this case it's 100 megabits per second that for the lowest 10% of the user. That's sort of our QoS goal. With that goal, and if you add the upper mid-band, you'll see a big increase. And also download speed, median download speed is 3x, is what we found out in our simulations. So this doesn't mean that you have to deploy upper mid-band and the lower band at the same time. Actually, because of the coverage enhancement that we have, this 6G at higher spectrum will match the coverage of the lower band. We put tons of emphasis into this coverage enhancement, so that operator doesn't have to either do NSA to help the higher frequency using lower frequency. It's not needed, or they have to couple these different frequency together. They could just upgrade their 6G if they want to, and decide to when to upgrade their 5G. They can take their time. There is no coupling between this new frequency band and the old frequency band. So, and with that, here's a summary slide in terms of specifically what we have, for this high efficiency G that we're talking about here. You can see the breakdown of, on the right-hand side, top right. This is FDD and TDD spectral efficiency improvement that you'll see. Like I said, 40 to 50% in these simulations, and in terms of coverage enhancement, what we're seeing is in the I think it's 2x to 5x in the uplink that we're showing. Yeah, and also there's what's important is cost efficiency. So we want to reduce the decoding complexity by a factor of 3. We want to reduce the memory footprint by a factor of 2, and we have designs to back it up. Of course, we also need to enable new services. The existing services in 5G, I think the most successful one, of course, is still smartphone, but there's also really important market growth in FWA and IoT. Those will be kept, but there are new device types that we're going to tackle, and especially for agentic AI. So in terms of services, connectivity is not the only thing. We believe operators are sitting on a pot of gold, and digital twin is a platform that will allow them to monetize everything they have. Instead of just transporting the data, the operators with their RF radio, they are essentially providing this digital infrastructure for the whole country or the whole city. And you could use the sensing service, right, for public safety purpose. And you can, digital twin will allow you to digest the RF sensing data. They could provide, logistic and the monitoring tracking services, right? So again, with additional information, for example, if you have a 3D map on the left side I'm showing, then you can actually improve the tracking service a lot better, right? So, and they could also be providing other sensing services, even for smart agriculture and for traffic monitoring, for many other services. Operator, you have a network that's covering the whole society, and it's up to the operator to invest in 6G and have an API that can allow them to provide that service. So here are some examples of what we have been doing. This is one example of network automation. Right? These are not revenue generating, but this does allow us to simplify the network operation. Right? So this is more of using AI for the network itself. But Of course, this is a one illustration of how we could aggregate all the data in the operator's network and expose the services. So this is one example of the sensing service, which is becoming more and more critical. I think everyone probably have seen, most of you probably have seen the drone detection trials, I think in many countries. And also, earlier this year in the MWC, we demonstrated drone monitoring using existing C-band base station as well, right? So, but it's not limited to drone, but for AGVs and many other use cases that's something that we already show. With that, let me hand over to Gavin to talk about 6G architecture. Thank you.
All yours, Gavin.
Thank you, Gabriel. Yeah, so I'll cover 6G architecture and then a brief intro to some of the ideas we are proposing around the area of security, and then, of course, conclusions. So in the area of 6G architecture, there's been a lot of interesting discussions externally and internally about the fact that in the day we've inherited the same architecture from the 2G, 3G over the last few decades. And the architecture is starting to look a little bit old in terms of like how it looks and how it's very much an appliance-centric solution. And a similar discussion is also being held around the protocol stack. So like SCTP and GTP were introduced in the 3G era and are still being used. And we're seeing, at least in our own internal prototest beds, as well as just what's happening in the cloud, that these protocols are starting to age and there's less and less support for them in these cloud native tools, which makes them much harder to evolve and harder to use and leverage the new changes that are happening. So we're seeing these things lead to things like high cost of ownership and making the operational upgrade more and more of a challenge. And so what we're looking to do is sort of see, okay, how can we transform these networks into a solution that is much more deployed in a way that allows the operator to leverage the cloud, leverage things, the tool sets in that ecosystem to enable them to create a much more robust network that is able to be much more flexible to deploy, minimize cost and complexity, and all the other kinds of advantages that they would like to have in order to make these networks much more both operationally efficient, as well as allowing them to introducing and monetizing new services. So the big question that we're asked around in the ecosystem is that, okay, you know that this is a problem. We see that this 2G, 3G architecture is aging. We see that these protocols, as I said before, are not supported. So how do we then go about and solve or move the platforms that operators use in their network to fully leverage a cloud native solution? And a good example of some of the things that we noticed during the 5G definition is things like Kubernetes and Dockers were not there from day one. And now we were stuck in this network functional virtualization paradigm, which was decided in the first study item during release 14. And it never changed since then. Once we decided to do that in the standards, it's pretty much been stuck in that same paradigm since then. Similar, we are now also seeing things like creating this mindset in the ecosystem of creating a specific 3GPP solution. For example, there's a lot of discussion, as you'll see in some of the later slides, on features, and Tingfang just mentioned as well, features like compute, agentic AI. These are features that are happening outside of the operator ecosystem. And what we would like to do is see how operators can incorporate them without necessarily creating a bespoke solution and changing it, because then you don't have the advantage of the scale and the evolution of these features. So we have these problems, and I guess MLOps is going to be one of the areas where this is going to be a big test on how the standard defines things. And so the question is, what do we want to do? So if we've been going around and talking to a lot of operators and vendors, and there seems to be a rough consensus that if I say to you, if you're going to wait till 2035, what do you want your network to look like? And there's basically everyone wants something that's essentially virtualized, cloud native, and is running on all these ecosystems, all these new cloud tools. The problem is when to actually make the switch. And that's where there seems to be a lot of tension in the ecosystem, is how quickly to move, because if we don't move soon, we're going to fall further and further behind. The best example of this particular topic is the RAN, because the RAN has changed the least in the last few decades. Obviously, we went from flat RAN we went from a hierarchical RAN in 3G to a flat RAN in 4G to a disaggregated RAN in 5G. But in the day, the functionality has pretty much stayed the same. There's been this essentially appliance-centric solution since the beginning the definition of the RAN. And so what we're thinking is that is it time for us to move to a service-based architecture of the RAN, where we then can now leverage all these new optimizations that a service-based architecture brings. For example, key things is basically the fact that we have a service-based architecture allows you to separate the concept of the endpoint independent of the physical location. So that allows us things to do benefits like connectivity, resilience, load balancing, high availability, to allow us to create a solution where the network can scale and be evolved in a much more flexible way. Now, this is important for the RAN itself, but it also is potentially important for some of the services that Ting Fang just mentioned, services like sensing and compute. If we want to enable these and host them towards the edge, towards the RAN, which would allow us then to have much faster latency, lower latencies, and much more benefit from this performance, we would like to then be able to create APIs and incorporate these services in a much simpler way, which APIs and service-based architecture allows. In the end of the day, what we would like to propose is a platform where the network is using the RAN, the core, and this SMO, the management plane, are now running on a cloud platforms where there essentially operators can choose which cloud they can use and leverage all these cloud services and cloud tool chains like AI, data processing, telemetry, etc., on their distributed or hybrid cloud platforms. So they potentially could use a central cloud, which could be public cloud, as well as their own telco edge clouds, and then distribute the RAN core management and all the new services that they enable to enable you to create a single platform and scale and move your workloads across these in a very clean way. So we see this as a key way to evolve the operator platforms to allow them to compete with the cloud players if they actually do want to host things like compute and AI, as we said before, and also allow them to make a much more operationally efficient and savings on these new platforms. So that's how we sort of see how the system will evolve in terms of how it is implemented. The next question is, what is the architecture, and what does the system work with respect to 5G? So one of the most contentious topics in the 6G discussion is, how does the network migrate from 5G to 6G? So as you know, or may remember, for 4G to 5G, there was the concept of having this non-standalone, which was essentially using 4G as an anchor and adding 5G as a supplemental carrier, which would then follow on with a standalone. And as we've seen mixed results in terms of how quickly or not at all operators have moved to standalone, there was general consensus that this was not going to be the approach for 5G to 6G. So the main proposal, which everyone is behind, is this idea of doing MRSS, or at least some kind of refarming, where you could take the low bands of 5G and you could share them with 6G. So you could use 5G and 6G in the same low band, similar to DSS, dynamic spectrum sharing, that was done in the 4G to 5G era. And so now your 6G device would be able to use some combination of whatever was reformed to MRSS or upgraded to MRSS, as well as the new 6G bands. Our feeling, though, is that probably will not be a sufficient solution, simply because there will be a lot of 5G spectrum, and it's not clear how many operators want to upgrade their entire band to support, at least to show a better user experience in 6G with a device switches to 6G. And so because of that, we think that there's a second solution that's needed. Now, the two solutions that are currently being discussed more on the plenary level than in the working groups yet so far is the idea of dual connectivity, which is the same idea that we had 4G to 5G, except now we think using a 6G anchor instead of a 5G anchor will at least hopefully solve the problem of having slow deployments and having operators be much slower to move to 6G core. And the other idea is to use dual stack. Dual stack is essentially, it can be standard, but it also could be a pure implementation solution where the device will connect using two separate stacks into the 6G, one for 6G and one for 5G, to allow then less impact to the operating network. So there's a big discussion as to which of these solutions makes sense, or even which one belongs in standards versus which one can be purely an implementation. Now, just looking at the device ecosystem, and this is kind of why we see dual stack at least being interesting from an implementation perspective, is that in the end of the day, dual stack will essentially eliminate, as you can see in the figure on the left, any coupling between the 5G RAN and the 6G RAN. So an operator can deploy, if it's all the complexities on the device, which will allow the device to connect to these two networks and have an independent network. We're also already seeing this kind of behavior with features like devices like dual SIM, dual active, where they're being used for things like gaming and also just to separate services based on subscription, to improve the user experience, but it's also how your device works today with wireless LAN. For the most part, your wireless LAN and your cellular are working separately, with the only real exception in practice is voice, where you need some kind of session continuity for IP. And so because of that, these kind of solutions are being used today. And so it is a potential from an implementation point of view, especially for networks where they do not have standalone 5G by the time 6G gets deployed, as an implementation. So we see these two areas being complementary, and we'll obviously see how that works in standards. In terms of the actual RAN, which is obviously the most expensive part of the operator network, there is relative consensus that most operators would like to, for example, for MRSS, reuse their 5G RUs for that solution. And obviously they will need to deploy 6G RUs for the new bands. And so our analysis and some of the features that Ting Fang was presenting earlier have shown that if there are any changes needed, hardware changes to the new 6G, they're most likely to be on the DU part of the stack, so not necessarily impacting the radio units that will be deployed. Our other analysis has shown that at least the frontal interface, the open frontal interface that's defined today in ORAN, is extensible to support all the new 6G features, such as sub-band full duplex, etc. So we see that the protocols being extensible. Now, you may still require hardware upgrades to support MRSS for a 5G, 6G DU, depending on which 6G features are deployed. And obviously that's going to be determined more and more late as we continue in the PHY part, the physical layer, in terms of the standard, to see what exactly does a 6G radio look like versus 5G, because that will obviously impact how much hardware impacts there would be to support a new 6G in these deployments. In terms of the core network, we have a three-part process: reuse, replace, and relocate. Relocate is on the next slide. And there is general consensus across the ecosystem that reusing as much of the 5G core as possible is what is desired pretty much by everyone for the 6G core. So there's certain things that are obvious to be reused. For example, the external interfaces, anything that the network uses to expose to application functions, etc., to allow them to manage the devices. That is something that should be RAT or G neutral in the first place. And so we expect those to be reused. Also, the internal core interfaces, if you're going to have a 5G, 6G core be an evolution of 5G, then you would want to use the same kind of service-based architecture. Although we would like to see something that we call protocol agility, which means that we don't want to be stuck with, let's say, HTTP2 TCP for the next 10 years if we reuse the 5G core. So we would like to see the ability for the platforms to evolve to these new types of transports and new applications, because those will then allow you to take advantage of these new tool chains as they arise. And obviously things like subscription policy, those are things that definitely can be used. The two key topics to be replaced are NAS and the RAN to core network. The RAN to core network I already discussed in the earlier slides with the service-based architecture for the RAN. If the RAN is service-based, then we would like to see that same service-based happen between the RAN and the core. And whether or not to use a new NAS is a big discussion. There is obviously the fact that the NAS protocol already works, and it's not clear, at least from anything we've seen so far, whether a new NAS is needed in terms of replacing it. But there are certain benefits and certain changes that we can make, like a modular NAS, which would allow a more efficient NAS in the 6G timeframe. It's just a question of whether that is worth the actual cost of deployment. So the overall 6G network will then look something like this. So on the right, you have the new 5G RAN and the new 6G RAN. The new 6G RAN, as we showed, at least in our proposal, is connecting using a service-based architecture to the new functions in the 6G core. And as I said, the new functions shown, the AMF and the session management and the mobility, would assume a new NAS. Again, this could be looking very much similar to connecting to a 5G core. There's definitely, as we show in purple, some of the functions that will be reused. And then the third element of this, which we call relocate. So 3GPP historically has always tried to put services in the control plane. The mindset being for the control plane is that operators own the control plane, so therefore they own these services. But there's a very good counterexample to this, which is voice. Voice has always been defined, at least voice over IP and voice VoLTE and voice over NR were defined in IMS using the user plane. And we see there obviously operators had a significant success in the user plane, defining services, voice services there. We do think then the new services, that sensing that was mentioned before by Tingfang, location, which has existed obviously since 3G, as well as AI, ML, compute, and the new data collection that everyone is defining to support things like digital twin, will be much better suited to run on the user plane for two reasons. One, we want them to work when the device moves out of 6G coverage. The user plane is an IP address, so it can work in any kind of RAT and doesn't need to be dependent on that. And so a good user experience for their customers, if they're running a sensing feature or maybe an AI compute feature, if the device moves out of 6G coverage, you want the feature to still work. And that means something running on the user plane is a much better solution. And the second thing is it then scales and works across every G, so that you don't have to then redefine these solutions every time you define a new G. So we do see simplifying the control plane would be essential to making these new services a success. So that's the architecture. Now I'm going to switch a little bit to the radio protocols themselves. So there's been very interesting discussions externally as we've presented this, of the idea that the fact that there's this really nice paper from the 80s called the end-to-end protocol, end-to-end concept, where it discusses the idea that if you have a protocol, things like reliability, things like security, if you have to solve them end-to-end, then you shouldn't be trying to solve them in each hop. And so if you look at the 3GPP protocols, they actually were designed without looking at this end-to-end principle at all. And so, for example, things like reliability, in RLC, you either have ARQ, which will repeat and repeat and repeat until you get RLF. So you either get the packet or the collection drops, or you have best effort where you get no reliability or no incremental reliability using ARQ. A lot of the protocols that were designed in this manner. And so they're over-designed to support features like reliability and also to support things like in-order delivery, etc. And so they were designed also in a way that's very simple to test and very predictable. So when the timer expires, you basically drop the packet, or you move the window, or some other feature depending on what it is. Or when you count a certain number of times, and then something happens. So it's very predictable and easy to test, but it doesn't work if you want to support large different kinds of device categories and across all different kinds of services and across all different kinds of contexts and applications. So we want to move away from this very easy performance-driven test, predictable performance, to allow to do something that's more flexible given AI. So now devices are becoming smarter and smarter. Our devices, as you know, in the field are already supporting kind of AI capabilities, things like traffic classification. And so given the ability of the device to have a greater understanding of its context, how can we then leverage that to then enable more performance? So what we have on the right then is this optimization of the user experience, where we still think and we still believe that the operator should have the ability to control the overall device behavior. So we have this idea of slow configuration, but then the device itself should then be able to adapt within that configuration to support these new kinds of scenarios depending on the context of the device. So what does that then look like in the protocol? So what we have is this original 5G and 4G as well, where we have these static values which are generally set to be the worst case network requirements and are fixed. They do not consider the application context, and at least what we're seeing in the field, that they don't change if the device is doing a voice call versus doing an internet download, versus doing XR, to a scenario where we allow the device to adapt. And instead of having a fixed value, we give the device a range and say, hey, adapt to that range within certain KPIs. So the way the device would then be able to work is that, let's say, for example, in-order delivery, which again is something that end-to-end should not be required to be end-to-end. The 3GPP link should not be forced to do in-order delivery because end-to-end on the internet is not in order. So let's say we now allow the device to have like a 1% out of order delivery. And then instead of giving the device, say, 1 second reordering time, but we could give the device a 1 second to all the way down to 100 milliseconds. And you can make that reordering time as small as possible as long as you achieve less than 1% reordering, as a simple example. So we go to what we call behavior-driven performance as opposed to fixed performance that's currently in the current system, allowing, again, a much richer experience depending on what the applications are running. Now, there are a bunch of other problems that need to be solved, and these are being discussed in the standard in order to allow the new 6G radio protocols and obviously all these AI use cases, The biggest problem is data collection. There, you want to be able to collect data across the device, all the core, RAN, etc., to enable not just the data lake for digital twin, but to enable the ability to do and create models for these analytics. In our view, the key idea in now, and this is there is no single one-size-fits-all solution. I don't know if you've seen some of the presentations or proposals like that were presented in the 6G workshop in March. We think that there's going to be very specific solutions depending on whether it's a device, the RAN nodes, or a legacy device, etc. But the key is then data access. So can you then make sure from this data lake that depending on which devices or what the use cases are, or who the third party is, allow that access to that data in order for them to train models and create models for AI use cases. The second issue is, okay, now you have a model. How do you then manage this model between the device and network to make sure they synchronize, that the device has the latest model, that it has been securely installed on the device? And once that is done, then the last piece is the actual management procedures. When these devices are running models in the field, you need to make sure the right monitoring tools are installed on the device, or potential feedback between the device and network, to make sure that the AI models are behaving within certain boundaries to ensure better performance. So all these kinds of difficult problems need to be evolved and solved by the ecosystem in the next few years in order to make sure AI becomes a reality. So in the end of the day, as I said already, the data collection, the key idea is not just is having high-level procedures to enable to access the data, collect the data, but then the key is to make sure that the access to the data is as broadly as possible, depending on the use cases. And then areas like MLOps, I alluded to earlier as well, this is a very new field. All the use cases, at least in our internal design, have been very use case specific. So to try to create a standard MLOps solution in 3GPP is going to be a mistake, because whatever is done today will be obsolete within a few months. And so what we would like to do is enable the system to leverage MLOps that is out there in the field and not worry too much about fixing the behavior in the standard. But the key to enable and make sure that the network behaves or performs best is to allow during the actual AI models inference to make sure that there is the proper monitoring tools in the network, in all the protocols, to make sure that the device is performing as specified. So that's a rough summary of where we see the device ecosystem evolving in terms of how the network architecture evolves, and also how we see the protocols incorporating AI as part of the basic operation. The last part, which is there's much more detail in our blog post, is where we see security moving in 6G. Now, if you look at the 6G workshop and all the presentations, there's pretty much consensus that we need to include security at the MAC. The MAC control elements today are sent over the air without security. And so as the MAC becomes more of a control link for how the device behaves, for example, activating certain types of MIMO configurations, activating CA, etc., we need to ensure that in order to ensure device security and prevent denial of service, that the MAC control elements become ciphered and integrity protected. There are other opportunities in native security to improve performance. For example, forward and backward security for mobility. So today there's only forward, there's no backward security. So changing how the key hierarchy works and where the keys are generated can improve that, as well as allowing this flexible security termination point. So you can terminate security all the way in the core if you want to run something like an IoT device, or you can host a security termination closer to the network, closer to the edge to, for example, allow a low latency compute use case. Allowing flexibility to this enables, and by separating how the keys are determined, allows the operator more flexibility in which services can be deployed in the network. Things like privacy have been studied in SA3 in the last few years, and so improving things like the RAN temporary identifiers, making those change more frequently, is something that we would like to also see as part of the security, as well as this SUPI privacy with symmetric keys. One of the interesting things, which is more moving to the bottom left corner of quantum safe security, is that for most of the security algorithms that are running the encryption of the PDCP, NAS, etc., the only change is really to switch from this 128 to 256-bit symmetric key algorithms. So we expect those to be based on the ETSI and the AES 256.05G. Those are all being developed outside of 3GPP, but we expect 3GPP to adopt them. But there are some procedures like SUPI, which use public key cryptography, and also, for example, we've seen proposals to do system information to do privacy or at least integrity for system information. The post-quantum crypto algorithms have incredibly large key sizes for the integrity, signatures for the integrity, and so there will probably have to be some changes if we are going to keep these public key solutions in the system if we want to make them efficient. The last part of security is then this robust trust framework. So we want to enable zero trust architecture, which is aligned with all the NIST solutions. So there, it's mostly about implementation, but there are some new reporting that we would have to do, as well as, for example, instead of using the signature system information reporting, we could do a robust security via a message digest, which is something is used in TLS. And it's all about essentially managing where the UE context and who has access and all those kind of things. A lot of it is about implementation, but there are some good best practices that NIST has recommended, which the system is slowly adopting to enable a most secure solution. So as shows in the QR code, there's our recent blog on this topic for security. So in the end of the day, hopefully we've given you a good idea of how mobile connectivity is evolving and how 6G is going to create these new opportunities for AI and other kinds of mobile experiences across these multiple platforms. Ting Fang obviously covered the improvements in coverage and capacity that we expect 6G to extend to, as well as how services beyond connectivity are expected to allow operators to monetize their networks in new and exciting ways. And then how the scalable architecture is essentially intended to improve the basically robustness of the network and how fast it can evolve, as well as the cost and also how new services are deployed. And then some incremental changes that we see being useful in network security based on robust trust and post-quantum solutions. We also have further videos available where we have more details on some of these topics on the internet and on YouTube. Thank you.
Fabulous. Thank you, Gavin. So we're going to go to some Q&A. We've got about 10 minutes for that. A terrific amount of material there. Yeah, so if you have a question, put it in the Q&A tab on your screen. We have a few already come in, and I'll put them to our speakers. They're both, as you can tell, they're both very technical and open to questions, so please do. Gavin, I'm going to start with one for you, though. You're putting a lot of ideas out there in this webinar between yourself and Ting Fang there, right? And you've got more, I know, in background. I just wonder if you could comment a little bit on the mood among your peers and in the ecosystem, the people you're kind of, talking to, working with, and so forth, as to how much consensus there is, where you're sort of agreeing and disagreeing, how much common terminology there is. Just give us a little bit of a mood check, if you would.
Okay, I guess I think Ting Fang and I should both answer that question because I think we have different moods from the different
I appreciate that's not a technical thing, but I think it's helpful at this stage.
Yeah, so I would say 3 years ago when everyone was proposing, like it was full-on crazy mode, like there were all sorts of very aggressive proposals and full-on changes. And then I would say over the last 2 years, there was a lot pushback and becoming much more conservative as to what is actually going to drive both reduce the TCO for operators and drive new revenues. And so I think that's been a healthy shift because of some of the challenges in 5G to actually look at what's going to actually drive revenue. So in that sense, I think the mood has kind of gone more conservative. But then at least what I'm seeing as we move towards the standards phase, like as the working groups start, I think there is a lot more interest now in generated in terms of actually doing something better. So I would say it's kind of shifted back towards doing more new things. Although I must admit it seems to be in more reserved areas. So, for example, the RAN architecture, there is not, as I said, there's consensus to do SBA at some point, but there's a fear to do it now. But I think so they're more concerned about what to do. But then around the RAN architecture, like data plane and all these other kinds of things, there is a lot more interest in doing new things to monetize the network.
Yeah. Okay. Thanks, Gavin. Ting Fang, if you're there, do you want to just give us a little bit of a gut check?
I think Gavin summarized the mega trend, right? So before the operators actually steps in, right? It's a lot of academia says sub-terahertz, this, and optical stat. So But once it became closer to the actual definition of the standards, people are much more realistic. But compared to a couple of years ago, where some of the operator bases says, "Hey, I have no money to deploy," now it's very, very different. Actually, there's so much excitement, in the air because they start to see, "Hey, I can get 50% gain just by updating my DU." That sounds like a great investment, right? And also all the AI buzz, right? That's hey, this is real. This is not something that you imagine. It's actually happening. They're seeing, this AI, driven new use cases, and I think there's just a lot more excitement as we come to the concrete designs.
Yeah, we've certainly, when you mentioned the 50% spectral efficiency gain, that made me pause and think. And there's comments in the questions here about it, and that's just with your analysis with a baseband upgrade. The RF install is the same.
Yeah. So yes, I think it's a 50% gain is not easy actually. I think a few months ago when I was giving a talk at the 6G workshop, right, in Korea, first thing I showed people is where is Shandong bound and where is 5G in a MIMO channel. We're 10 dB away, right? So that's basically, for people who understand communication theory, 10 dB is huge, and getting 50% gain off a baseline that's 10 dB away from capacity, it's not that hard, right? It requires new thinking. It requires fundamental changes in modulation, in waveform, in MIMO, right? So there are many fundamental changes that are needed, but it's all DU, right? So it's all baseband processing that can enable this big change. So, but we care even more about is the coverage, right? So we're showing like 2x to 5x coverage gain on the uplink, which is a huge deal.
Yeah, also massive on coverage. Okay, we're running tight here, but there's one that's sort of it's almost a bit too easy for you, Tingpan. It's hard, but it's not a setup, I guarantee it. I'm going to combine two questions into one. So one is, with increasing power consumption needed for AI, do you expect 6G devices will be able to handle this power consumption? The other question is, what AI edge cases require 6G? So I guess there's a little bit of a link between them. It's
So in terms of the AI we're running on the phone, yes, it does requires power, but it's, nowadays if you look at your phone, right, it's already have a lot of smart, like either Gemini or some other ChatGPT and all those use cases. On the phone, it's not a challenge. To be honest with you, I don't think phone is a problem. The biggest challenge I'm seeing is on the glasses. On the glasses, the battery size and the power consumption, thermal requirements are much tighter. So those are the challenges we have to tackle. One way to tackle it is transfer those AI beefy 100 TOPS processing through 6G to the edge devices. If you have a puck in your pocket or a phone in your pocket, it's easier, right? And then that puck can use 6G to connect to the network as well, right? So that's sort of one way to do that. And what AI use cases require 6G? This is a very interesting one, and the most obvious one is because you need a lot of uplink in all these agentic AI use case. You have to stream a lot of media for the AI agent to work on. So those will require the 6G link to substantially enhance your uplink capacity and uplink coverage.
Yeah. Okay. Good stuff. There's quite a detailed question on uplink actually in here, but I'll ask your team to contact you after, just because it's a bit much to deal with now. Question for you, Gavin. Could you talk about the where or when the 3GP timeline for the 6G core will be finalized? So I guess we could broaden that out, and that's a sort of an architecture question, really. What are your thoughts and expectations? We hear about 6G standalone essentially from day one.
So yeah, there's consensus with that, and that's one of the reasons, for example, if there's the need for a dual connectivity solution in the RAN, we would prefer the 6G anchor, so the device will always be connecting to the 6G core. The question of when the study item will pretty much end at the same time as RAN 1. So there's a 1.5-year study, and then with the to release 21 is I think 1.5 years as well. So in the next 3 or 4 years, we will pretty much have a new 6G core at the same time as the physical layer. The other question is just how different it's going to be, and that's probably going to be the most in terms of how much it impacts deployments. If the NAS is, as we said before, reused, then there's very little changes, and it's more about these supplemental services like compute, sensing, etc. in the 6G core. And obviously, there's much more ability then for operators to accelerate at least the services, because their basic core will be already available for them on day one before, from the 5G experience.
Yeah. Okay. Good stuff. Hey, we've come right to the top of the hour. We've got a bunch of questions we can't get to right now, but where appropriate, I'll ask the Qualcomm team behind the scenes to review them and get back to you. There's some good ones here. Thank you for putting them in. I wish we'd have put them soon, and I'd have got them in there. But with that, we've hit the top of the hour. We must close. Just remains for me to thank Gavin Horn from Qualcomm. Thank you, Gavin.
Thank you, Gabriel and Catherine, for organizing this.
And Ting Fan Ji as well. Ting Fan, thank you.
All right. Thank you, Gabriel.
With that, we're going to close the call, but thanks everybody for attending. Thank you and goodbye.
Okay. Bye-bye.